Scalability in distributed and parallel computing. What is scalability? Scalability refers to the ability of a computing system to handle increasing workloads efficiently. As demand grows, a scalable system can adapt by adding resources without affecting performance, reliability, or availability. Scalability ensures that system performance remains consistent even when the number of users or tasks increases. It allows organizations to expand their systems gradually by adding resources only when needed, which helps reduce operational costs and avoids over-provisioning. Additionally, scalability improves system reliability by using replication and load distribution, ensuring that workloads are balanced and failures are minimized. Now let's look at the first type of scalability, called vertical scaling, also known as scale-up. Vertical scaling means increasing the capacity of a single machine by adding more resources, such as CPU power, RAM, or storage. In this approach, the system continues to run on the same server, but with upgraded hardware capabilities. One major advantage of vertical scaling is that it is simple to implement, because the application architecture usually does not need to change. However, vertical scaling has a limitation, as there is a physical limit to how much a single machine can be upgraded. For example, upgrading a server from 8 GB of RAM to 32 GB of RAM in order to handle more users is a common case of vertical scaling. The next type of scalability is horizontal scaling, also known as scale-out. Horizontal scaling increases system capacity by adding more machines or nodes, rather than upgrading a single server. In this approach, the workload is distributed across multiple servers using a load balancer. Each new node handles a portion of the total processing load, which helps improve performance and reliability. Horizontal scaling is especially suitable for very large systems and ensures high availability, because if one server fails, others can continue to operate. For example, adding 3 new servers behind a load balancer to manage increased web traffic is a common example of horizontal scaling. Scalability in parallel systems is all about improving performance by adding more processors or cores within the same machine or a tightly connected system. In this setup, the workload is split into smaller tasks, which can be executed at the same time. However, scalability is limited because the processors share memory, cache, and buses, which can create bottlenecks. Also, the serial portions of programs, as explained by Amdahl's law, restrict how much speedup can be achieved. Parallel systems are best suited for compute-intensive tasks that run within a single machine. It's important to note that maximum speedup is restricted, and adding more processors beyond a certain point may not improve performance. Scalability in distributed systems refers to improving performance by adding more independent machines, nodes, connected via a network. Each node has its own memory and OS, reducing shared resource contention. Provides high scalability, horizontal scaling, by distributing workload across nodes. Challenges include network latency, communication overhead, and data consistency. Suitable for large-scale applications like cloud computing, distributed databases, and web services. Examples: AWS/Azure Cloud Clusters, Cassandra, Hadoop, Microservices Architecture. Client-server architecture is a computing model where a central server provides services or resources, and multiple clients request and use these services over a network. In this model, clients send requests to the server, for example, to access data, perform computations, or retrieve files. The server processes these requests and sends responses back to the clients. It also manages resources, databases, and security in a centralized manner. Communication between clients and the server usually happens over TCP/IP or HTTP protocols. This architecture can be scaled by adding more servers, which is called horizontal scaling, or by upgrading the server's hardware, known as vertical scaling. The advantages of client-server architecture include centralized management of resources and security. It is easier to maintain and update applications. Data storage and processing remain consistent across the system. Additionally, it supports controlled access for clients. However, there are some disadvantages and limitations. The server represents a single point of failure, so if it goes down, clients cannot access services. Performance can drop when many clients connect at the same time, creating a server bottleneck. Scalability is limited unless multiple servers and load balancers are added. Finally, the system depends on a stable network connection between the client and the server. Microservices architecture is a design approach where an application is divided into small, independent services. Each service performs a specific business function and communicates with other services over a network, usually through APIs. The application is divided into multiple loosely coupled services, for example, a user service or a payment service. Each service runs in its own process and can be developed, deployed, and scaled independently. The services communicate using lightweight protocols such as HTTP, REST, gRPC, or messaging queues. Databases may be specific to each service to maintain independence. Scaling is achieved by replicating individual services rather than the entire application. The advantages of microservices architecture include independent deployment, meaning services can be updated without affecting the entire application. It enables continuous integration and continuous deployment, or CI/CD, making frequent updates easier. Microservices also support polyglot programming, allowing different services to use different technologies. However, there are some disadvantages and limitations. Managing multiple services, APIs, and communication can be complex. Service-to-service calls over a network can introduce latency and slow down performance. Maintaining data consistency across all services can also be challenging. Peer-to-peer, or P2P, architecture is a decentralized network model where all nodes, called peers, are equal. Each peer can act as both a client and a server, sharing resources directly with other peers without a central authority. In this model, each peer can request and provide resources, such as files, data, or computational power, to other peers. Peers communicate directly over the network, typically using P2P protocols like BitTorrent, Gnutella, or blockchain protocols. Adding more peers increases the network's overall resources, including storage, bandwidth, and computation. No single node controls the network. Instead, peers collectively manage resource discovery, sharing, and updates. Data and services are distributed across the network, which reduces the chance of a single point of failure. The advantages of peer-to-peer, or P2P, architecture include high scalability, because adding more peers increases the network's capacity. It is fault-tolerant, meaning there is no single point of failure, and the network can continue to function even if some peers leave. P2P networks also make efficient use of resources, utilizing the idle resources of all peers. However, there are some disadvantages and limitations. Maintaining data consistency across all peers can be difficult. Security is a concern, as controlling access, authentication, and privacy is harder. Network management, including search, discovery, and routing, can be complex. Finally, P2P is not suitable for centralized control or mission-critical systems. Applications of scalable systems. Scalable systems are widely used in cloud computing platforms to dynamically allocate resources based on demand. Large-scale web applications rely on scalability to serve millions of users simultaneously without performance loss. Big data analytics systems use scalability to process massive datasets efficiently. Distributed databases and storage systems depend on scalability to handle growing data volumes reliably. High-performance parallel computing applications require scalability to solve complex scientific and engineering problems.